Hello, my name is Marion Sudvarg. I'm from Washington University in St. Louis, and I will be presenting a concurrency framework for priority-aware intercomponent requests in CAmkES on seL4 that was co-authored with Gill. In component-based software engineering, components are used to both encapsulate and isolate state and functionality in a system. The diagram here illustrates an example component specification for a drone system. Notice that each concern of the system, including the interface with various pieces of hardware, as well as control algorithms, is compartmentalized into its own component. Components provide structure, modularity, and reusability. This makes it easy to modify pieces of the system. For example, if an accelerometer needs to be changed to a new piece of hardware, this can be achieved quite simply by swapping out the corresponding component without modifying the overall system design. Components define interfaces for communication and control flow. So, for example, an accelerometer might provide interfaces by which to calibrate the corresponding hardware or to pull its current values. Motor components might provide interfaces to set the motor speed. For this work, we consider real-time component-based systems. A component might originate a timer or event-driven task. For example, a component encapsulating camera functionality might pull the camera imaging sensor at a given rate. Tasks may then share common functionality or state, which is then encapsulated within connected shared components. So task execution begins in the originating component, but then proceeds via synchronous remote procedure call invocations across the shared components. In this example here, a job is released at every polling period of the camera. Execution begins in the camera component where the sensor is read, but then control flow proceeds to a shared object detection component. If an object is detected, an event might be logged to a database or file before a reply is sent. So in this work, we are specifically targeting the CAmkES component framework, which runs on top of the seL4 operating system kernel. seL4 is a formally verified capability-based lightweight microkernel, which supports real-time and mixed criticality systems. Because seL4 is secure and lightweight, it is used as a resilient OS platform in real-world systems, including the Boeing unmanned Little Bird H-6U, which is pictured here. CAmkES is a component description language and framework for seL4. It provides component procedure interfaces for remote procedure call requests. The seL4 kernel provides a primitive called an endpoint, which is a synchronization point for threads to wait for messages from other threads. CAmkES assigns each CPI a single thread that waits on an underlying endpoint. This thread is assigned a static priority, which is specified in the component description and set at compile time. So the problem here is that this is not well suited to task execution that crosscuts components. If tasks of different priorities concurrently send requests to the same CPI, the semantics of priority-based preemptive scheduling are broken. So because CAmkES and seL4 lack full support for hard real-time tasks, executing end-to-end in this way across multiple components, we have extended CAmkES with a concurrency framework for priority-aware intercomponent requests. Even with our framework, RPC invocation overhead is not significantly increased, and all code for our extensions is available from my website, which is listed here. So our extensions are intended to be easily adopted into existing CAmkES-based systems and easy to use when designing new systems in CAmkES. They do not change seL4's verified code base or the existing CAmkES software. They require minimal changes to the existing CAmkES component specifications, and we provide macros and compile time checks. Our extensions remain fully in user space and support both reentrant execution as well as locked critical sections over shared state. We are able to bound overhead under our framework by using priority semantics to guarantee consistency over lock acquisition without additional atomic operations. Our framework targets implicit deadline sporadic hard real-time systems using fixed priority preemptive scheduling on a unicore. Tasks and dependent shared components must execute on the same core, which means that both unicore and fully partitioned multi-core systems are supported. We currently support closed trusted systems. For components encapsulating thread-safe reentrant shared functionality, we provide priority propagation, and for components encapsulating shared state, we provide priority-based shared resource access and locking protocols, including the Non-Preemptive Critical Sections protocol, the Immediate Priority Sealing protocol, and the Priority Inheritance protocol. So for CPIs encapsulating shared functionality, we support priority propagation, under which execution should be at the priority of the requesting task. To accomplish this, our framework couples task priority with request messages, and the corresponding thread bound to the CPI sets its own priority to the task priority before running its procedure. Additionally, execution should be preemptible if requested by a higher priority task. To realize this, our framework provides each CPI with a thread pool size according to the number of possible concurrent requests, and this guarantees that threads are available when a request is sent. Additionally, the threads wait at the priority ceiling of all requesters, which guarantees that preemption can occur. Our framework also allows CPIs to encapsulate mutually exclusive execution over shared state. In other words, to have their execution constitute a locked critical section. Locking and priority-based access protocols are managed fully within the component through our framework, allowing the CPI to encapsulate both the locking semantics and functionality over the shared state without having to use separate mutex or other locking services. Our framework provides two static priority locking protocols, the Non-Preemptive Critical Sections and Immediate Priority Sealing protocol. Under both protocols, a CPI is assigned a single thread, which implicitly prevents concurrent execution over the critical section, since if the thread is executing, it is not currently available to respond to other requests. Under NPCS, Non-Preemptive Critical Sections, the thread is assigned the maximum system priority. But NPCS suffers from inflated worst-case blocking times. For IPCP, the Immediate Priority Sealing protocol, which has comparatively better worst-case blocking times, the thread is instead assigned the maximum priority among all possible requesting tasks. And this is sometimes referred to as the highest lockers priority, or HLP. So because both protocols use a single thread at a static priority, this is implicitly supported in CAmkES, but our framework allows these protocols to be declared explicitly. For our implementation of priority inheritance protocol, similarly to priority propagation, our framework assigns a pool of threads to the CPI endpoint, each waiting at the highest locker's priority. When a request is received, the thread receiving the request checks a non-atomic Boolean lock variable. If the lock is already held, the thread checks the priority of the lock holder, elevates it if necessary, thus allowing for priority inheritance, then waits on what we call a notification manager, which I will explain in the next slide. However, if the lock is free, the thread acquires the lock, registers the request priority and a pointer to its thread control block, then demotes its priority to the request priority and runs the CPI's procedure. Once done, it releases the lock and signals the notification manager. If a thread is waiting on the notification manager, this thread will then wake up, pop itself from the notification manager, and proceed to acquire the lock and run the procedure. So our framework provides this user space object called a notification manager. The reason being that the seL4 kernel provides a primitive called a notification object, which is a binary semaphore that can serve as a lock or a signaling endpoint. The problem with the notification object is that by default, threads are awakened in FIFO rather than priority order. Even under the seL4 mixed criticality systems kernel, which does wake threads in priority order, the notification object is structured as a linked list, which has poor asymptotic behavior. We instead provide the notification manager, which implements a priority ordered heap. Each thread is bound to its own notification object, and these are ordered according to the task priority of the request received by that thread. When the notification manager is signaled, the signal is vectored to the notification object held by that thread with the highest request priority. Then this thread can wake up, remove itself from the heap, and proceed as it needs to proceed. Our framework also supports nested locking, which is achieved simply via nested RPC request chains among CPI's encapsulating locking protocols. Absence of a cycle among request paths implies deadlock avoidance. CAmkES can actually generate a system digraph representation in the dot language, which makes it very straightforward to detect possible deadlock. In our current framework, our priority inheritance protocol implementation can only send requests to static priority CPIs, not to other CPIs encapsulating priority inheritance protocol or priority propagation. But this does follow a common technique of using more strict protocols for nested locks. Under round-robin scheduling, threads of equal priority may preempt each other. seL4 implements round-robin scheduling by default, which breaks the semantics of priority-based shared resource access. For example, a non-preemptive critical section running at the maximum system priority may actually be preempted by another thread of equal priority. So to address this, under round-robin scheduling, we use priority laddering. Tasks are assigned even priorities, while shared resource CPI threads are assigned odd priorities, which will either be the maximum system priority in the case of non-preemptive critical sections, or the highest priority among possible requesting tasks, +1. So this does restrict us to 128 instead of 256 priority levels in seL4, but this is still more than the 100 priority levels available in Linux and should be sufficient for most real-time task systems. To measure the overhead induced by our framework, we measured RPC request times on both an Intel x86-64 platform and a Raspberry Pi Model 3B+. We found that RPC invocation times under our framework remained under 6 microseconds on Intel and under 16 microseconds on the Raspberry Pi. When compared to base CAmkES RPC invocation times, which were around 3 microseconds on Intel and around 7 microseconds on the Pi, we see that our framework does not introduce substantially more overhead. Additionally, we measured the overhead of our notification manager, which exhibits good quasi-linear growth as the number of waiting threads increases. Even for 100 waiting threads, total time to wait and wake a thread remained under 540 nanoseconds on Intel and under 680 nanoseconds on the Raspberry Pi. We also evaluated our framework using randomly generated synthetic task sets according to the component configuration illustrated here. Each task set consists of 3 tasks, which are dispatched periodically by dispatcher components. These dispatcher components register periodic timers with a time server. So for this, we designed a custom implementation of the CAmkES time server for the Raspberry Pi 3B+. We provide code for this with our implementation. The 3 task components send requests to 2 shared components, component A and component B, illustrated here. We evaluate 3 configurations of these shared components, one in which A and B both propagate priorities, one in which A and B both use the immediate priority ceiling protocol, and one under which A propagates priority, while B uses the priority inheritance protocol. For each configuration, we randomly generated 10 task sets for each utilization in 0.1 to 1.0 and steps of 0.1. This resulted in 300 task sets to be evaluated. To easily evaluate each task set in succession, we implemented a hierarchy whereby a root dispatcher dispatches each task set one at a time, dispatching one only after the previous one has completed. So after performing this evaluation on both the Raspberry Pi and the Intel x86-64 platforms, we observed that no tasks missed their deadlines. So in conclusion, we have provided new extensions to CAmkES on seL4 that support priority propagation for reentrant CPIs, while also allowing CPIs to encapsulate priority-based locking protocols without the need for additional atomic operations. Our framework supports hard real-time behavior for cross-component task execution. We intend to extend our concurrency framework to allow for nested priority inheritance protocol, to support asynchronous event notifications, to continue to improve our framework's ease of adoption, to reduce false positives in deadlock detection, in other words, to identify when a request cycle does not necessarily imply deadlock, and to enforce behavior over untrusted components in open systems. Thank you very much for listening to my presentation. I will be available afterward for any questions.